Standard divide and conquer algorithms like merge sort come with a specific architectural overhead. Because merge sort cannot sort within its own bounds, it requires a complete auxiliary copy of the data, effectively doubling the memory footprint during the execution phase. Quicksort provides an alternative. It is the primary choice for memory-constrained systems because it is designed to sort data strictly in place. Instead of splitting the array down the middle, quicksort centers its logic on a single element called the pivot. The algorithm partitions the remaining data around this pivot, shifting smaller values to the left and larger values to the right through a series of internal swaps. Because these swaps occur within the original array indices, the algorithm requires nearly zero additional memory beyond the space it already occupies. To understand why quicksort is favored in systems engineering, we must deconstruct its partition mechanics, trace the recursion tree, and calculate the mathematical risks of its time complexity. The pivot is the element used to divide the workload. Different implementations may select the first, last, or middle element, or even a random index to serve as this baseline. In this 5-element array, we will designate the first element, 50, as our pivot. The partition process compares every other element against this 50. Values smaller than the pivot move to the left flank, while values greater than the pivot move to the right. This results in a partition state. The values 20, 10, and 40 are grouped together on one side, while 60 is isolated on the other. The pivot sits exactly between them. This illustrates the most important property of the algorithm. Once the partition is complete, the pivot has reached its final sorted position. It is permanently fixed and will not be moved by any future operations. Quicksort is essentially the process of finding the final home for one pivot at a time, ensuring that every step results in incremental progress towards a sorted array. Let's trace a full dry run using a 7-element array, starting with 8 as our initial pivot. The algorithm scans the array. Since 3, 1, 7, 0, and 2 are all smaller than 8, they are routed into a subgroup on the left side of the pivot. The value 10 is greater than 8, so it is isolated into a separate subgroup on the right. With the 8 locked in place, the algorithm now applies the same partition logic recursively to the unsorted subarrays on either side. Zooming into the left branch, 3 becomes the new pivot. It partitions its remaining elements, moving 1, 0, and 2 to its left, and 7 to its right. The recursion continues until it reaches the smallest possible subarrays. Here, 1 becomes a pivot, separating 0 and 2 into individual nodes of length 1. When every recursive call hits these single-element base cases, the process is complete. The tree structure ensures that the entire array is now fully sorted. Implementing this requires 2 distinct functions, working in a coordinated control flow. The quicksort function acts as the orchestrator. It takes the array and its boundaries, first performing a check to ensure the lower bound hasn't surpassed the high. It then calls the partition function. This is where the physical swapping occurs, and it returns the index where the pivot eventually settled, which we store as p. Now the recursion begins. The function calls itself to sort the subarray between the low boundary and the index immediately before the pivot. Then it executes a second call to sort the subarray starting immediately after the pivot up to the high boundary. In this architecture, the partition function is the engine that alters the data, while quicksort manages the branching logic. Because the workload depends on the pivot's final position, the time complexity of this algorithm can vary significantly based on the input data. In the best-case scenario, the pivot always bisects the array into 2 equal halves. The resulting recurrence relation, T of n equals 2T of n over 2 plus n, is the same as merge sort. This balanced division results in an optimal time complexity of n log n. However, the algorithm is susceptible to a worst-case scenario. This occurs if we pick the first element as a pivot on an array that is already sorted. Because there are no elements smaller than the pivot, the partition is completely imbalanced. We end up with a subproblem that is only one element smaller than the original. We are forced to process n elements, then n-1, and so on, until we reach the end of the array. This linear degradation shifts the efficiency from logarithmic to quadratic. In this worst case, performance hits big O of n squared. Regarding space, while we don't use auxiliary arrays, the system must still store the recursive function calls on the stack, requiring O of log n memory on average. While the quadratic risk is a mathematical reality, using a random pivot selection ensures that real-world performance almost always maintains the n log n average. To decide when to use quicksort, we have to evaluate its defining architectural traits against the requirements of the system. Its primary advantage is its in-place nature. By performing swaps within the existing array, it avoids the memory overhead required by other divide-and-conquer methods. But this efficiency comes at the cost of stability. During the partition, elements are swapped across large distances based on their value. If two elements have the same value, like these two 50s, their original relative order can be lost during the move. This is the fundamental engineering trade-off. You gain low memory, high-speed execution, but you lose the ability to maintain the original order of duplicate elements. By understanding these mechanics, you can choose the right tool for the specific constraints of your data. In the next session, we'll see how these traits hold up when quicksort is matched directly against merge sort in a head-to-head comparison.